now that we understand what a line integral tells us, it tells us the extent to which the vector field that we're integrating aligns with the velocity vector of the parameterized curve that we're traveling and integrating along. Right? Now that we know that that's what it means, we want to build some tools for actually computing the values of these path integrals. And so the next 2 or 3 sections of the text are devoted to that. And true to form in any math class, we tend to do everything first the hardest and most explicit way possible, and that's going to be the way we're going to do it today. And then in tomorrow's class, we're going to see that in some cases, we can get away with doing a lot less work and not having to worry about parameterizing a curve and then computing everything explicitly. But that's only going to be the case when we know that the integrals are path independent. In other words, when it doesn't matter how we get from point A to point B, it just matters that we're starting at point A and ending at point B. So when I have path independent integrals, we can do a lot less work to find the value of a path integral. But if we don't know that, if we can't take that part for granted, then we are, at least for now, forced into doing what we're doing in this section. And that is to explicitly take the parameterization of our curve and use that parameterization to compute the value of a path integral. So this is section 12.3 in your team folders for today. And the first activity in this section sort of dissects the process of how we might come up with a way to use the parameterization of a curve to compute the value of a path integral. And so rather than, I originally planned to have you do parts of this activity, but I think maybe we can just talk through this one together so that we have some time to actually practice the strategy that ultimately arises out of doing work this way. So in this first activity, we have a vector field which has components xy comma y squared. So that's what's being visualized here. And then we have these 3 linear path segments, C1, C2, and C3, oriented in the way that's shown here on the picture. And so the goal is going to be to figure out how to compute the path integral along each of these sides, the C1 side, the C2 side, and the C3 side. So what we should be able to do, according to how this activity has us begin. So if I want to focus on the bottom side for a minute, the C1 side, what we notice is that every point on that side has a y-coordinate equal to 1. And so if we're just traveling along that bottom side, the only y values that we're going to see are the y value 1. So my vector field, at least as far as that segment is concerned, my vector field is not going to be xy comma y squared. It's going to be x times 1 comma 1 squared. Right? So it's just going to have the value x comma 1. So that's just a single variable. There's only one variable that affects the value of the vector field along that path because the value of y is a constant. And so if that's the case, then that ultimately lets us do the following. That because along that path, the vector field is just equal to x comma 1. And dr, this little infinitesimal vector element along the tangent direction to my parameterized curve, is only going to have an x component and not a y component. So we call that x component dx, but the y component is equal to 0. And so when I take the dot product of the vector field with that element of tangent vector along the parameterized curve, what I get is x1 dotted with dx0, which gives me just x times dx. And so the value of the path integral along that side of my triangular path over here is just going to be the integral of x dx, where my x values range from x equals 1 to x equals 4, because that describes the left and the right extent of the x values along the path C1. And so the integral is just going to be the integral of x from x equals 1 to x equals 4, which is a pretty straightforward integral to evaluate. It gives us a value of 15 halves. So if we do a similar thing for the path on the right, the C2 side, that path resides in a vertical line, and that vertical line has the equation x equals 4. Right? All the x coordinates of points along C2 are equal to 4. And so along that side, we find, along x equals 4, we have f of x and y is equal to, well, it's xy comma y squared, except that now we're setting x equal to 4. And so my path, my vector field, is going to only vary with the single variable y, and it's going to have the formula 4y comma y squared. And we also have that dr, which is dx comma dy. Because my x value isn't changing, my x value is a constant, this dx is just going to be 0. Right? We are only moving in a vertical direction, so we only have a dy. We don't have a dx in that direction. So that f dot dr is going to be 4y times 0 plus y squared times dy. So it's going to be y squared dy. And the y values of the points along this side range from y equals 1 up to y equals 3. And y ranges from 1 to 3. So the path integral along C2 it has the following form. So all we need to do is integrate y squared dy, y ranging from 1 to 3, and that gives me the value of 26/3 for the path integral along the right side. So if we take stock of what we have so far, the path integral on the bottom side ends up being 15/2, 7.5. The path integral on the right side gives us a value of 26/3, so that's 8.6 repeating, right, as a decimal. And so the next interesting question is, what happens if we go directly from point A to point B, right? Directly from 1, 1 to 4, 3 along this diagonal side? How would the work look different? And so this problem sort of walks us through a process of computing that path integral by first writing an equation for that diagonal line, the diagonal side of this right triangle, using slope-intercept form, y equals 2/3 x plus 1/3. And then evaluating the vector field by substituting 2/3 x plus 1/3 in for y. And that gives me, yet again, a vector field with only a single variable dependence, and that's a dependence on x. Right? But then when it comes time to find dr, which is equal to dx and dy, we have to use the fact that dx and dy are related together by the slope of that line, 2/3. So every dy is 2/3 as much as dx, because that's what the slope of that line is. And so dr becomes dx comma 2/3 dx, or in other words, 1 comma 2/3 multiplied by dx. So when we take the dot product of f with dr, we end up getting the value, the vector field evaluated on y equals 2/3 x plus 1/3, and so it has kind of this nasty formula, dotted with 1 comma 2/3 dx. So we do that dot product. We write it all out as a function of x. We integrate that from 1 to 4. It's a little bit nasty. We come up with 151/6 as the value for that path integral. So 15/2 on the bottom side, 26/3 on this side, and 151/6 if I go directly from 1, 1 up to 4, 3. So now comes the interesting question. Well, an interesting question. There are many. And the interesting question is, how are those values that we found here related one to another? So just to recap so far, we found that the integral along C1 was 15/2. The integral along C2 was 26/3. And the integral along C3, the diagonal side of my triangle, was 151/6. So there were my 3 integral values. And so is there a relationship between these various values? Well, what do you think? When we did the airplane example in the preview activity for the last section, we sort of talked ourselves into, well, maybe it doesn't matter how we get from point A to point B. Maybe I should get the same path integral if I go directly from A to B versus if I have a stopover over here and then continue along the way. Right? So maybe I should get the same total value by taking both the red and the green legs compared to just taking the purple directly. So let's investigate that. Is it true that if I add 15/2 and 26/3, well, let's see what we get. So common denominator of 6. And so 15 times 3, what's that, 45. 26 times 2, that's 52. And so I'm going to end up with 96/6. That actually reduces pretty nicely. So reduce that by 3, and it's going to give me 32 over...
Should it be 97?
Yes, you're right, 97, so it doesn't actually reduce. Thank you. 97/6. So it actually doesn't give us the same thing as if we had gone directly from point A to point B. which in itself is potentially an interesting observation, right? So here we see a clear example where this integral appears to be path dependent, not path independent, because I ended up getting more work done on me by this vector field by going directly from point A to point B along C3, compared to if I went from this point to that point along C1 and thence to this point along C2. So tantalizingly, the last question that's asked of us in this portion of the activity is, can we say anything about the vector field itself? Is F a gradient vector field? And why or why not? So this is a nice callback to yesterday, because this was what we were doing at the end of yesterday's class, thinking about how we can tell when a given vector field is or is not a gradient vector field. And so what would we say, what would we want to say here about F and whether it is or is not a gradient vector field? And remember that the formula that we have for F of xy, is xy comma y squared. So what did we do yesterday to try to assess whether or not a given vector field is or is not a gradient? What were some options? So the most expedient way to tell when something is not a gradient vector field is to subject it to the screening test. And the screening test says, take the y partial derivative of the x component and the x partial derivative of the y component. If it's true that this thing really is a gradient, if it really is the gradient of some scalar function h of x and y, then that means that the x component would be the x partial derivative of that h, and the y component would be the y partial derivative of that h. And so that if I take the y partial of the x component, I'm going to get the xy mixed partial derivative of h. And the x partial of the y component would be the yx mixed partial derivative of h. And as long as those two are continuous functions, they should agree with one another in the case that this is a gradient vector field. But if they don't agree with one another, then it is impossible for this thing to be a gradient vector field. And what we find out is, at least in this example, when I take the y partial derivative of the x component, I get x. When I take the x partial derivative of the y component, I get 0. And therefore, since those two things are not equal, we can say for absolute certainty f is not a gradient vector field. There is no such function h of x and y that has as its gradient our vector field. So this is a real success of the screening test. The screening test can tell you right away if something is not a gradient vector field. And so for us, the interesting question is, now that we know that this isn't a gradient, does that have any relationship to the observation that we made here, which is that this path integral ends up being path dependent? So that's going to be our job for tomorrow, is to figure out what is the connection between those two observations, right? Should it be the case that whether or not a vector field has path-dependent or independent path integrals have anything to do with whether that vector field is a gradient vector field? So that's going to be the main subject of what we talk about tomorrow.